Hello students, in this video we'll discuss about finite state automata model or finite automata model and its representations. In the last video we have discussed about introduction to languages and operations, and we have done with all the operations, but let me continue with the complement. I just introduce that. Let me go with the example of complement. Okay. So what's of all, the complement is denoted with the L power C. It is nothing but universal language minus the language whatever you are going to take, right? So for example, if my language is A comma B, I'm taking a different alphabet. The universal language is nothing but all the possible strings of AB. Everything, it's like Akshaya Patra about A comma B. It will give you everything whatever you want with the AB. Like zero length, that is very important, guys. The dangerous string in the ALC and CD is epsilon, because zero length, whenever it comes, zero length means epsilon. So star means 0 to infinite, so 0 means epsilon will come. Then one length means take sigma one time. Two length means concatenate sigma with the one length, right? Just do it, you'll get the two length. One length concatenation one length, you'll get two length. Like A concatenation A concatenation B, AB. Same way B with AB. So BA, BB. Now I got the two length. To get the three length, just concatenate the AB with the two length. So you'll get the three length. Like A concatenation with all, just keep the A in front of the two length. AAB, ABA, ABB. Same way you can take the remaining, right? Then for example, you take any language, right, over the alphabet, any language over the sigma, that language must be either subset or equivalent to sigma star. So you can conclude in this way that, so this is the sigma star over the language or over the alphabet, then the L is somewhere else we are going to have. Either it should be subset or equivalent, then L complement is nothing but from the universal language, just remove the language. So if something in language, then must not be in the complement. If something in complement, must not be in the language. So I can conclude that L intersection L complement is empty set. So if a string is not in the L, must be in the complement, or if a string is not in the complement, must be in the L. So the string over the A comma B must be either in the L or L complement. So then I can conclude that L union L complement is sigma star. Then if I take some language like L, right, even length strings, if I take like that, even length strings, then automatically what will be happen, this length is 0, length is 1, length is 2, length is 3. So you have to take only even length, then it will be having epsilon AB, BA, BB, right? Same way 4 length A, so on. So what is the L complement? Then from the universal language you have to remove the L, the difference of universal language and L. Then what could be the L complement? Then epsilon is not in the, if epsilon in the L, then don't take the epsilon in the complement. AB are not in the L, then you must take into the complement. Two length are already in the L, so don't take it. Then three length are not there, so AAB, so on. So this is nothing but odd length of strings. This is about complement, guys. So as I told you, the definition of formal languages also, it should have the grammar and automata, machine, something like that, and restrictions and alphabet. So the second definition of automata is, it is a mathematical representation of formal language. First of all, how the automata works, right? Let me go with the model first. Finite automata model. So it is having three components, guys. First one is input tape. So this is input tape. The length of the input tape is finite or infinite, sometimes depends on the string, but assume that now finite. And of course this is denoting the starting symbol and ending, but there's not, is, it's not constant, depends on the textbook. They are having their own starting and ending symbols, and generally we don't have such a concept in general reference book whatever we are following. And this is readable, we cannot change the symbols of it. So this tape is completely readable tape. You cannot change it. And we are going to have the read head. Okay. So it is going to read the things. Of course, it cannot write the things, right? It's only going to read the content of this input tape. And this head moves only in unidirectional, right? The tape is unidirectional tape and it's going to read it. Of course, where we are going to have the write, that is a common model we have taken here, but especially from the finite automata, we are not going to have the write. I'll tell you when it is going to be right also. We'll discuss that. Then now at a time it can read only the current input symbol, right? For example, if it is A here, then A. And whatever it has taken, it is going to forget. And when it goes to the next symbol also, it forgets everything, whatever it has taken. That's why we say that there is no auxiliary memory in the finite automata. We can conclude, we can say that no auxiliary memory. It won't remember anything. And I usually say that this is a memory loss patient. It forgets everything when it goes to the next symbol. That's it. Then this finite state control, or the finite state, the right machine, which is going to control the movements of the tape and head. So if a string is given, it will tell you based on the movements of head and input tape, the final output is whether it is accept or reject. This will discuss more about the things. So we are having mainly three components: tape, head, finite control unit, or finite state control. We can generally call it as finite control unit. Finite control unit. Then let me take some example of finite automata for this, which language, what it is going to be, that we'll discuss in the next video, how to construct an automata for a formal language. So just let me introduce the terminologies related to the finite automata in this video. Every finite automata is denoted with 5 tuple: q, sigma, transition, q naught and f. The q is nothing but set of states, and see the word finite. No automata in the market is having infinite number of states. And sigma is denoting the alphabet. Of course, the definition of alphabet itself contains the finite. And q naught is called as initial or starting state. And every automata is going to have exactly one starting state, no zero, not more than one. And a set of final or accepting states, right, which is subset of q. Of course, you may have 0 final state, 1 final state, 2 or even more final states in the automata, but starting state must be exactly one starting state, but final state can be any. And the transition function which derives the edges of it, so the q into sigma tends to q. We'll discuss about this later, definitely, what exactly the meaning of this, right? So means, of course, let me go with this. What are the states we are having here? q1, q2. Okay, let me write it here. So this is automata. Let me show what are these, right? Q states. The states are represented with the circles. Then I can say that q1, q2, q3. And the input alphabet means the names of the edges, 0, 1. The starting state is denoted with the empty arrow. It is nothing but q0. Sorry, q1 here. And the final states are nothing but double circles. So here we are going to have q3. Then transition means, see, on q0, if I read 0 where we are going, q0 only. See, q1, sorry. q1, 0 where we are going, q1. Then same way, q1, 1 where we are going, q2. That means on any state q, if you read any input symbol 0, 1, then it will give you one more state from the queue. That's the meaning of the transition function. Whatever the transitions we have taken, that we are representing here, right? So there are three representations of finite automata. One is transition diagram, where the states are represented with the circles, and starting state is denoted with the empty arrow, and final state is denoted with double circle. I told you in the last slide how it is going to be. And the input symbol is denoted with the D. As I told you, only one starting state, one, right? Then that is going, even the second representation of finite automata is transition table. The same diagram, transition diagram, can be represented with the transition table. Here the table is having rows and columns. The number of rows are nothing but the number of states. Here the states are x, y, z, and the starting state is denoted with the empty arrow and final state is denoted with the star. In some textbooks, circle in another textbook. It depends on the textbook. So both star and circle denotes the final state in the table. Then on x, if they read 0 where we are going, x 0 we are going to x, that I'm saying next. X1 where we are going y, like y0 we are going to z, y0 we are going to z, y1 we are going to x. Like just whatever the transitions you have represented here, that you have to represent as a table. That's it, nothing more than that, right? So and we have one more, like in the finite automata representations. So other than these two, we'll be having a instantaneous description. Descriptions. We generally call it as ID. What does it mean? See, a movement of finite automata is depending on the two things. See, for example, if I say that if I read 0 where we are going, then you must ask a question that on which state, because x0 we are going x, y0 we are going z, z0 we are going y. So you must say that first question is which state, right? The current state. Now I'll tell you, on x if I read an input symbol where we are going, then immediately you'll ask which input symbol, because reading 0 going to x, reading 1 we are going to y. So the movement is depending on the current state and the current input symbol. Generally we'll go with the two only, but in some cases, especially in OU, they are going to ask in terms of IDs only. Then where we are going, so x0, now where we are going x, then it will give you the next state, like whatever we have taken, right, in the last video, tuple notation, q into sigma. So same thing here. Here the states are denoted with the sigma, right? Q, and input symbol is sigma, then next state is q. You can write it same way. X0 where we are going to x. Same diagram we can represent like this. X1 where we are going, y. Y0 where we are going to z. Y1 where we are going to x. Z0 where we are going to y. Z1 where we are going to z. But here you have to specify externally what is the starting state, like so qs is x and f is z, like you have to mention, because there is no representation of it. And what is it, why we are calling it as instantaneous description? Because we are specifying a single instance of the machine. That is the meaning we are saying that instantaneous description of the finite automata. Hope you have understood the three representations of finite automata. So in the next video, as I told you, how we got this automata, for which language you have constructed it. If you get such questions, then all those things will be addressed by the finite automata construct, means next video. We'll discuss what would be the approach and how we are going to do it.